Welcome to day 38 of our object-oriented programming course. Today we will be diving into the concept of multi-threading, learning about threading, its benefits and best practices. Let's get started. Multi-threading allows a program to perform multiple tasks concurrently within a single process. Threads are the smallest unit of execution and share the same memory space, making communication between them more efficient. This approach helps improve CPU usage, especially when performing IO-bound tasks, and is perfect for tasks that can run in parallel without interfering with each other. Let's take a quick look at the differences between threads and processes. Threads are lightweight units of execution within a process, sharing the same memory space. On the other hand, processes are independent programs, each with its own memory space. Threads are generally more efficient than processes because of their ability to share resources quickly, but they come with their own challenges. Python makes multithreading simple with the threading module. This module allows you to create and manage threads in your program. For example, here we define a simple thread that prints numbers from 1 to 5. We create a thread using the thread method, start it with start, and use join to ensure the main thread waits for the new thread to finish before continuing. Synchronization is crucial when multiple threads access shared resources. Without it, you risk data inconsistency. Locks, also known as mutex, help prevent this by ensuring that only one thread can access a resource at a time. In the example here, we use a lock to ensure that both threads print numbers safely without interference. Now let's talk about deadlocks. A deadlock happens when two or more threads are waiting for each other to release resources, causing the program to come to a halt. To prevent deadlocks, we should lock resources in a consistent order and use timeouts to avoid threads getting stuck indefinitely. Managing a large number of threads can be inefficient. Instead of creating new threads every time, Python offers thread pooling with the thread pool executor. By defining a pool of threads, you can easily distribute tasks to available threads, improving the efficiency of your program. The example here demonstrates how to use thread pool executor to run tasks concurrently. When working with multithreading, be aware of common issues like the Global Interpreter Lock or GIL, which can limit Python's ability to execute CPU-bound tasks in parallel. Another common issue is race conditions, which occur when multiple threads try to access shared data at the same time. The best way to handle this is by using locks or other synchronization mechanisms. To work efficiently with multithreading, keep a few best practices in mind. Minimize shared resources to avoid the need for complex synchronization. Use synchronization mechanisms like locks to prevent data corruption. Optimize with thread pooling to avoid the overhead of creating too many threads. Finally, always profile and test your code to ensure performance is not being compromised. Now let's put what we have learned into practice with a hands-on activity. Your task is to create a multi-threaded program that fetches data from multiple URLs concurrently. Use synchronization with logs to manage shared resources and then optimize your program with thread pool executor to handle a large number of tasks efficiently.